Hello, welcome to a new series on non-commutative geometry and non-associative extensions through naive class theory. In part 0, we're going to cover the motivation for non-commutative geometry as well as non-associative extensions. The history of classical differential geometry is an extraordinarily rich one. In 1827, Carl Friedrich Gauss released one of his most groundbreaking theorems called the Theorema egregium, in which he formulated the notion of surface curvature being an example of an intrinsic geometry. This launched the modern foundational study of geometries that are independent of embeddings. Years later, in 1854, an astute mathematician by the name of Bernhard Riemann conducted a famous habilitation lecture in which he formally introduced the notion of a Riemannian geometry, which he would go on to formulate further, of course. Our modern understanding of manifolds stems largely from the consequences of this event, where Riemann yielded upon us the realm of Riemannian metrics and the Riemann curvature tensor. This result laid the groundwork for future theories such as Einstein's general theory of relativity. For his 1869 breakthrough, Elwin Bruno Christoffel released a paper introducing Christoffel symbols, formally expressing how we can compute covariant derivatives and geodesics. During the span of this time, especially in the late 1800s and early 1900s, other major contributions entered the picture. For example, Gregorio Ricci Carbastro, along with his former student Tullio Levi-Civita, formulated the absolute differential calculus we now refer to as tensor calculus or tensor analysis. This enriched the language of curvature and allows us to induce covariant derivatives on manifolds with a more rigorous language. Entering the 1900s, differential geometry exploded to become a highly respected field in higher mathematics. At this point, we surpassed the year of 1899, where Élie Cartan had already developed the exterior differential calculus and improved the rigor behind the mathematics of moving frames. Lie groups and algebras had been formally integrated into differential geometry as a result of his work. This was only the beginning of differential geometry, however. In 1918, Hermann Weyl generalized the Levi-Civita connection for conformal manifolds. The theory of connections on principal bundles exponentiates in popularity as a result. Ultimately, this culminated into the studies of mathematical gauge theory and topological K-theory. These studies, intrinsically influenced by the fascinating discoveries of one of my personal heroes, Emmy Noether, strongly underpin the backbone of many modern developments in theoretical physics and physical chemistry. In 1945, classical differential geometry and the growing theory of differential forms had been formulated into a unified fundamental theorem of calculus in n dimensions by Élie Cartan through an equality called the Stokes-Cartan theorem. This miraculous theorem, generalizing the earlier works of Lord Kelvin, George Stokes, Vito Volterra, Edward Jean-Baptiste Goursat, and Henri Poincaré, established a benchmark upon which modern differential geometry is understood and measured. In 1984, David Hestenes would reformulate this theorem in the language of Clifford algebras, showing how the theorem also holds in frameworks outside of tensors and differential forms on manifolds. This reformulation of the Stokes-Cartan theorem through variations and direct sums of k-vectors known as multivectors is dubbed the fundamental theorem of geometric calculus. Entering the mid to late 1900s, theories of global differential geometries emerged through Chern classes, sheaves, abstract algebras, and differential topologies, establishing a bridge between differential and algebraic geometry. Differential geometry, already encapsulating such a rich framework, was then connected to index theory through the Atiyah-Singer index theorem. The culmination of these works unified differential geometry with topology and analysis. However, we simply cannot neglect the influence of quantum theory throughout the 1900s, because by the 1920s, Paul Dirac began speculating about non-commutative coordinates and how this would impact the structure of geometries. Differential geometries were also beginning to be formulated in terms of Hilbert space representations of non-commutative C-star algebras during the years that followed. Further advancements in this direction would yield extensions to de Rham cohomology through cyclic and Hochschild cohomologies. But by the 1980s, Alain Connes formulated a generalized Dirac operator called a spectral triple, defined in terms of an operator algebra, a Hilbert space, and a self-adjoint differential operator. Around this time, many researchers began realizing that their studies of quantum groups yielded another perspective for which to consider non-commutative geometries. These quantum groups were discovered to be essential to non-commutative geometry as Lie groups are to classical differential geometry. Connes' work, influenced by earlier works on operator algebras from von Neumann, Galfand, Neymark, Segal, and more, has itself been extended by even further developments in non-commutative geometry. In 1982, Michel Hilsum collaborated with Connes to formalize the notions of singular spaces and stacks through groupoids, foliations, and their operator algebras. Beyond this, however, Sean Majid would go on to develop the concepts of braided geometries by cross-product quantum groups and duality principles between quantum groups and non-commutative spaces. These new ideas were summarized in his landmark text entitled Foundations of Quantum Group Theory in 1995, opening the doors to the study of algebraic non-commutative geometries. It was also during these times that Connes and Chamzadine were investigating how the standard model Lagrangian density could be derived from a fluctuation of the Dirac operator over a generally non-commutative product space. John Mador would also go on to develop fuzzy spaces and matrix approximations to geometry, useful for finite dimensional non-commutative geometries and attempts to formulate mathematical field theories called quantum gravity. As it stands in 2025, there exist multiple ways to formulate a non-commutative geometry, and multiple avenues for further generalizations have been strongly hinted at throughout virtually all of these methods. One may indeed be concerned about which extension to differential geometry will naturally emerge beyond the non-commutative realm. In this series, we will be discovering non-commutative geometry from the ground up, assuming familiarity only with multivariable differential calculus and linear algebra, although the vector calculus of Gibbs and/or the geometric algebra of Clifford are especially useful. All other necessary elements from other theories, which there are, in fairness, many of, will be motivated and explained on an as-needed basis. Ultimately, the goal is to not only build up non-commutative geometry, but to extend differential geometry to an even higher theory of non-associativity. To the extent that we may lack associative composition and an identity element, we will consider the implications of generally incoherent homotopies in terms of a pre-categorical meta-theory that we shall, for now, refer to as naive class theory. This final section of the series will begin to ponder concepts of coherence and incoherence as they relate to the concepts of locality and non-locality within mathematical universes, hinting that non-commutative geometry itself is a localized fiber emerging under projections that occur upon a generally non-associative and non-unital global prespace. Thanks for watching this introduction on the history of differential geometry and motivations for non-commutative geometries and non-associative extensions, and I hope to see you in the next video, in part 1, where we begin covering differential graded algebras, the bedrock of how we're going to begin this formulation.